So, hello everyone, welcome to this NEASQC webinar that will be dedicated to quantum computing and CO2 capture. I am Pascal Bernier-Brunner. I'm the dissemination leader for this project. And we have with us today Wassil SENNANE. Wassil, can you go on to the next slide, please? So, this webinar is one of a series that's aimed at early users. And our objective is to help the quantum community discover and test the libraries and tools that we make available. And another objective is to get your feedback. So we are really interested in having your feedback. We have monthly webinars and we're going to have them every month until the end of next year. So we already had one last month. It was also about chemistry. And we are going to have one in November about quantum probabilistic safety assessment. So if you're interested, registration is open. In December, we'll talk about benchmarking, and here again, registration is open. And then we'll have other subjects, financial applications, quantum natural language processing, measurement optimizations, and much more. I mean, we'll cover all the use cases of our project. So can you go on to the next slide?
Yeah.
So today's speaker, Wassil. Welcome, Wassil. It's nice to have you today. So Wassil works at TotalEnergies. He's a multidisciplinary engineer, and he currently works as a PhD candidate with Sorbonne University in Paris. Also, there are more resources concerning today's subjects. We have published various publications. So you have the titles here. I will send the slides to everyone, so you will have the slides. Also, we have an open source library that's on the NEASQC GitHub. So generally speaking, I mean, all our use cases have publications, open source resources. So if you go to our website, very easy, neasq.eu, on each use case page, you can find all the publications that we have issued and the links to our GitHub. So, I mean, feel free to consult it. So, Wassil, it's your turn to speak. I will fade out. And yeah, sorry, one point, your questions are very welcome, but we'll take your questions at the end of the webinar after Wassil's presentation.
Thanks, Pascal. So, as you said, so I'm Wassil SENNANE. I'm TotalEnergies PhD student between TotalEnergies and Sorbonne University. And this talk is entitled Quantum Computing and CO2 Capture, so trying to apply the quantum computing techniques to the CO2 capture problematics. And as Pascal said, we published some papers and the library. So this presentation is gonna present what is doing by the library and some result that we obtained thanks to this library. So I'm just gonna give some information, some context. There is a very promising class of porous materials for the CO2 capture, which is called metal organic frameworks. So they are constituted of, so if you go into the unit cell or unit pore, you see that, and there is a structure constituted of metal ions or metal complexes. And these metal complexes, they are linked to each other with organic-like molecules, which gives metal organic frameworks. Their advantage is that you can tune them very easily by changing the metals, changing the atoms, changing the length of the organic linkers. This allows you to determine selectivities, but also change the pore size, which has a direct impact on which molecule you want to capture. And in our context, we are interested in capturing the CO2. So with this tunability, you can build a lot of metal organic frameworks, a lot of MOFs, and you can build databases of that. However, to understand better the behavior and the CO2 capture into these MOFs, we aim to calculate the granted energy of a MOF plus CO2 system. To do that, some methods already exist, such as FCI calculations, which are giving exact energy within a certain basis set. However, they're just impossible to be done with this complexity of size. The atoms and the system are too large to proceed this kind of calculation. And other classical methods, however, they could be realistic in terms of complexity in terms of operations. They are most likely going to fail if the system is not exactly at its equilibrium, or for some reason they can also fail. So quantum computing is expected here to merge the grades of the two worlds. We expect from quantum computing to yield very accurate results for any geometry of any chemical system, and with a reasonable complexity. So quantum computing alone, you have to have some algorithms to apply it, because it's not automatic at this time, at least. And the algorithm in which we use the quantum computing or quantum computers is the version of quantum eigensolver. So this algorithm is at the center of the library we produced and the result I'm going to present after. So it consists on, first you start with a molecule. This, the user gives as an input a molecule. From this molecule, you build its Hamiltonian in the second quantized form. This Hamiltonian, then you map it into a qubit language Hamiltonian. That means that your Hamiltonian is translated from a second quantized form to a sum of weighted Pauli terms. This sum, the advantage of that is that this sum of weighted Pauli terms can be measured on the quantum computer. So next step, so we are here. Next step is going to the QPU, the quantum processing unit. And on this QPU, one create psi state, an initial state, a state, which is parameterized. And this is equivalent to creating a circuit and to parameterize its gates. With this circuit, we measure the qubit language Hamiltonian, and the result of this measure is an energy. So both the parameters with which we parameterize the circuit and the energy are sent to a classical processing unit that is going to proceed the optimization, thus proposing new parameters to be measured. And there is an optimization loop that is made in order to obtain the ground state energy. So in this case, so the optimization is a minimization loop. So we want to minimize the energy, because something very interesting we have with this method is that any energy we measure here will always be greater or equal than the lowest eigenvalue of the Hamiltonian, which corresponds to the ground state energy of the system. So by minimizing it, we expect to reach this ground state energy. So the library produced is available on GitHub, and it's called NEASQC Deep 4.2, and it's organized with 3 scripts, or let's say 2 + 1. So the first script in this package is GitHub calc hamilton.py. The second is GitHub calc energy.py, and the third one is test H2 molecule. So GitHub calc hamilton.py has the role to calculate and to prepare the Hamiltonian objects during the VQE algorithm. The GitHub calc energy.py have the role to prepare the circuit, proceed the optimization, and makes the energy measurements. And the test H2 molecule.py is a quick tutorial for using the VQE I just presented on H2 molecule very efficiently with those 2 packages. So the library is organized as follows. Only 3 scripts is quite simple to use. And we can divide the VQE algorithm within these 2 scripts. So you have the GitHub calc hamilton.py, which manage this first part, and GitHub calc energy.py, which manage the second part. It has to be noted that so in the test H2 molecule.py, you see that they are very synchronous in terms of behavior. Like the output of this script are directly given to the input of this script, which directly gives the energy. But also, these 2 scripts can work separately. If you want only the first part, or if you need only the second part, because you have the other, or you want to work within another context, you can, thanks to this library. So, as I said at the beginning, so we made a publication from which the results, you can very easily retrieve them with this library. So this article is entitled Calculating the ground energy of benzene and the Special Deformations with Noisy Quantum Computing, and we published it in PRA. So in this article, we worked with benzene. Briefly, why benzene? Because So the initial context is the carbon capture in metal organic frameworks. And some of the organic linkers of MOFs are benzene-like molecules. So either they are only benzenes or sometimes longer benzenes. So it had sense to analyze the behavior of benzene with more precision. At the same time, benzene has a quite simple geometry because everything is symmetric, but it's still a 42 electron system. And with the simplest chemical basis set available, it requires 72 qubits to be fully modeled on a quantum computer, which is very far from the capabilities of both our in-house simulator that comes from Atos, which is a quantum learning machine that can simulate up to 30-35 qubits exactly, but also the actual hardware, they cannot deal with 72 qubits. So this molecule, by just giving the geometry of the atoms and the chemical base that you want to, the GitHub calc-hamid.py will directly build you the Hamiltonians that you require. In addition, I said that we need to reduce the number of qubits because 72 qubits is too large. So what we made in this study, we proceeded an active space selection strategy. So instead of taking into account all of the orbitals, we focused only on the orbitals which were near the homolumoga. Same, so here, instead of working with 72 qubit systems, we worked with systems from 4 to 16 qubit, which is much more easy to simulate, although it was a bit difficult because the calculations were still big, but it was much more easy and it opens the way to making more calculation and more benchmarking. And same than before, this active space selection, you can do it very easily with the GitHub calc-hamid.py script. Moreover, what I can add also is that we wanted to, so as I said in the introduction, some classical methods, we know that they will fail because they do not provide some guarantees when the system is not really at its equilibrium. So we wanted to test this VQE algorithm on the benzene, but also on regions in which we know that classical methods will fail because they are far from their equilibrium geometry. So we defined some special deformations that we apply to benzene. We refer to that as distortion in the paper. The paper also is available on arXiv. I can say also that. So we define 3 types of distortion of physical deformation of the benzene to test if our VQE algorithm is able to yield the correct results for different geometries of the system which are not at the equilibrium. And same, so here to have this procedure with GitHub calc-hamid.py is very easy because you just have to parameterize your own geometry. But if you want to retrieve the exact benzenes we worked with during this paper, we put the built-in functions to directly have the geometries we worked with. So it will be very easy for you to recover the results if you want. So now when we have the VQE, so I spoke about the first part. So now we have the geometries, the chemical set, the number of orbitals. So we have all of the Hamiltonians we require to make all of the calculation. Now we have to investigate the QPU side. And the QPU side, so as I said before, you have to prepare a state psi that is parameterized. And for creating this psi, which is equivalent to creating a circuit, there is multiple methods. And we studied 2 of them in our article. Then there were the hardware efficient method and the quantum multi-hypercluster cluster method. So hardware efficient method consists on manually designing your own circuit. So you create a pattern that you can duplicate by modifying its depth and so on. And you manually design it in order to be easily implementable. On the other side, the quantum multi-hypercluster cluster method is a chemically inspired method. So it directly depends on how Hamiltonian you are treating. We know that, and we know before doing anything that it will produce quite long and quite deep circuits, and that will be at some point very noise sensitive. You can switch between these 2 circuits, there's 2 methods with the GitHub calc-energy.py script. And on top of that, it will be very not difficult for you to trick the hardware efficient method to make any hardware efficient method you want, if you want to have a different circuit than what we use in the paper. So the main result we obtain in this article, I'm not going to present everything, but I'm just going to first sum up and show them some some of them. So we first designed 3 types of hardware efficient circuits, and we compared them in a noiseless regime and also in a noisy regime. So I can add now that the structure of the code is made for noiseless simulation. However, because of its compatibility with the Atos QLM machine, it's very easy to add a noise model by just changing one line. So you can do that with documentation of the QLM, of my QLM. It will be very easy. So we compared hardware efficient results, 3 types of circuits on the noiseless and noisy regime. Then there, between these 3, there was one which was much better than the others. We took this one and we compared it to the UCC results. Then we analyzed a bit at the optimization occurring in the UCC method. We tested the scalability of the method with increasing number of qubits. So this was allowed by the GitHub calcami.py script by changing the size of the active space. And we compared the quantum computing technology methodologies and the classical methodologies on recovering the energy, but also other parameters such as the natural orbital occupation numbers. After the review, so we sent this paper and then there was a review. After the review, we added extra stuff. We improved a lot and we added a much better influence of the noise on the results. So we studied this noise influence on the results and provide some interesting informations. And we added also real experiments on IBM-Q quantum computers. This also is simple to be done. One requires an access to IBM-Q processors. It's obvious, but just with the token you have when you register and 2 or 3 lines of compatibility with that Atos QLM, you can very easily send all of calculation on a real quantum computer with this library. So first, I'm going to speak about the comparison between the hardware efficient circuit we selected as the best and the unitary coupled cluster method. You can see the pattern of the hardware efficient method. It's not so interesting here, but you can see its pattern on the paper. So 2 first columns are hardware efficient results. The 3rd column is the UCC results. The 2 first ones differ by the depth. So depth equal 1, depth equal 2. I just multiply by 2 the pattern of the hardware efficient ansatz and see what are the results. Note that all of these 9 subfigures, they concern results obtained with the 8 qubits Hamiltonian, because the results are long to obtain for larger qubits also in the noisy regimes, but I'm going to speak about that later. The blue curves on all of these subfigures are the Hartree-Fock energies, so the kind of the basic classical method to compare with that we choose. And all of the references of energy, so the EREF, are the exact energies. So we took the 8 qubits Hamiltonian, we diagonalized it, which is also available with the script, to have the target energy, the one which the energy we want to reach with this VQ algorithm. I'm also adding that the orange curves are an average of 50 VQE experimentation. So we processed the VQE 50 times, and the orange curve is an average of the results we obtained through these 50 experiments. The first line are noiseless results. The UCC are not changing, so there is no variance in UCC, and they converge very, very well. However, we see that around the equilibrium, which is denoted by the red plus here, it converges a bit better in this area than for extreme deformations. Because I didn't say, but the x-axis is R1, and the R1 parameter is the parameter of the distortion 1, which was the most extreme, and it was much more interesting to investigate this one than the others. But we made all of them in the paper. For the hardware efficient circuit, we see that it's not working at all everywhere. It works for extreme deformations and giving very interesting results. However, around the equilibrium and sometimes before, it just totally not working, because either it stops at the Hartree-Fock or it's higher in energy than the Hartree-Fock, which is not something we want to have. We note also that going from the depth equal 1 to depth equal 2 here, from this to this increasing of depth doesn't increase the quality of the results. So changing the depth on hardware efficient circuit has not every time a sense. Something also which is obvious, I could have said at the beginning, but I say at the end, is that you see that there is box plots. So with whiskers, that denotes that there is a variance on the results. So this variance comes from the fact that when doing the VQE algorithm, you have to prepare upside state, and because you are working on the CPU side with a classical optimizer, this classical optimizer needs an initial guess of parameters. And for the 50 VQ experiments we made here, we took 50 times a random initial guess. So this shows that this hardware efficient method is not robust against optimization, because optimization can induce some errors. Not all the initial guess converge towards the same minimum, which is a big issue on this circuit, and it can yield a very inaccurate results due to that, a very big ovariance due to these optimization issues. The second line, so yeah, and I can also add that this is not something you see with QCC, because QCC, the initial guess is very precise, and it's a chemical inspired one, is the MP2 initial guess. On the second line, so these are the same noiseless results. However, we included shot noise at the end. So the shot noise is the measurement noise. We select the finite number of them, and we saw directly that the hardware efficient ansatz are very, very impacted by this shot noise, sorry. You see that it's even worse for not extreme deformations. And even for extreme deformations, it's becoming very worse regarding the noiseless case. So hardware efficient circuits are very shot noise sensitive, although we could expect that it's still outperforming the Hartree-Fock energy for extreme deformations in this area. On the UCC-SD ansatz, the quantum Mutaika cluster ansatz, we see that the variance is much more controlled, and all of the results are still very well converging, or they are very close to the exact energy, and they still very outperform the Hartree-Fock energy, which is a good result, which means that we expected the UCC to be very noise sensitive, and it's not sensitive to shot noise. It's very robust against shot noise, which is a good information to take. On the third line, what we made is that we, in addition to this shot noise modelization, we added an idle noise model. So we implemented during the calculation amplitude damping and pure dephasing process by just changing one or two lines in the code. So these are called the T1 and T2 noise. I refer you to the paper if you want more details. But it's a modelization of the hardware noise, the decoherence noise that occurs when doing a real calculation on real QPUs. It appears that the hardware efficient results that are not really changed by implementing this hardware noise when there was only shot noise on the second row, which confirms that the hardware efficient method is hardware efficient in terms of decoherence, but we discovered that it's very shot noise sensitive. On the UCC side, this is what we expected. The method is not at all robust against hardware noise, and it makes all of the results becoming very worse, and having no results are converging, or even giving an outperformance of the Hartree-Fock method when there is a very common hardware noise modelization. These were the results we obtained for this paper, and as I said, you can retrieve all of them with the package. It's very easy to retrieve the first line and the second line also by just changing one parameter at the end. The third one, you need to trick the QPU variable of the package to implement this hardware noise model effects, and this is very easily and very easy to understand thanks to the documentation of Atos. This picture shows you the evolution. So I'm just gonna, okay. On the y-axis, there is the energy minus ERF. The reference is the exact energy of the 16-qubit systems. The three subfigures, they change by the number of qubits they represent. So the left figure represent results obtained with the 8 qubits Hamiltonian. Then it's 12 qubits here and 16 qubits at the right. On the y-axis, on the x-axis, sorry, it's still the R1 parameter, so the distortion of the system. What we wanted to denote here is our method really scalable or not? So what we made the hardware efficient and UCC calculations. VQ is 50 times, except for the QCC we made only once because of the variance which is non-existent, which doesn't exist on noiseless regime. And in blue, it's still the Hartree-Fock energy. For the three graphs, the three pictures, the reference is the 16 qubits energy. because it's the lower. So the exact energy of 8 qubits is greater than the energy of 12 qubits, which is greater than the exact energy of 16 qubits. So there is the more you increase orbitals, the more you decrease your energy. And we saw first that the UCC results, which we know are working quite well on 8-qubit system, they follow the evolution of the system on 12-qubit system, by giving decreasing energies here. However, these UCC results going from 12 to 16 qubits, they not necessarily decrease, and for areas in which it's not working as well as around the equilibrium, so for extreme deformation here and also there, it's not working as well, and it gives increasing results from 12 to 16 qubits. So from there to there, it's not necessarily following the evolution of the system. For the hardware efficient method, where it works, so for extreme deformations, it follows the evolution of the system. And for some deformations, for bigger systems, it converges faster than the UCC ansatz. However, around the equilibrium, so in the areas in which the hardware efficient doesn't work, the error which is made is increasing with the number of qubits, so it becomes more and more inconsistent. So why do we see that from 8 to 12 qubits an amelioration, but from 12 to 16 we don't see an amelioration, and the results are worse? We interpret this by optimization issues. So the molecules like benzene, they can be really well described with the p orbitals, and all of them are taken into account when dealing with 12 qubits. That's why from 8 to 12 qubits, we have a big increase of energy. However, from 12 to 16 qubits, the user, so us, we added orbitals into the active space, which were already well described when frozen. So the user knows, however, the VQE doesn't know, and it will spend its limited number of optimization steps in optimizing orbitals, which does not require to be optimized, which can explain why we have a much worse conversion for bigger systems, for bigger number of qubits than for 12 qubits. So this would be also an issue on the VQE. The VQE, as it's composed today, cannot really know which orbitals were well described when frozen, which one needs really to be optimized. So this is something interesting that we showed on that article. So now I'm not going to speak about a whole deformation, so not about all of the distortions we studied, but I'm going to focus on, for this slide, for Hamiltonians around the equilibrium. I'm still working with 8-qubit system and only around the equilibrium. So what we made here is a study of the noise influence. So instead of taking only one noise model as we did before, we processed the whole VQE for different values of T1. So you know that there is the amplitude damping characteristic and the pure dephasing characteristic T2. We put T1 equals T2, if I remember well. You can check in the paper because it depends on the definition you have of T1 and T2. But we set T2 as a function of T1, and we made only varying T1 to say, okay, how is behaving the VQE algorithm when changing the hardware noise influence, instead of just being between noiseless and the noise model quite close to the real hardware. What is between these 2 points? What is the behavior between these two regions? So we proceed the VQE algorithm for different values of T1. And the green and the gray curves, and so not the curves, so all of the curves, I'm going to be more clear, all of the curves are an average of 15 VQE experimentations for different values of T1. And the shaded area is the min-max amplitude for each of these T1 and T1 values. On the left column, there's our hardware efficient circuits. On the central column, still hardware efficient circuit, and on the right column, UCC. So the two first column, the green result and the gray result, they differ by the initial guess. In the green curve, we took 50 times different initial guesses with the random initial guesses as before. However, for the central curve, the hardware efficient in gray, we took 50 times the same initial guess of parameters, which was just the zero guess. So we took all of the parameters equals to 0 as an initial guess. The first line, all of the results were obtained with 1,024 shots, and the second line, 4,096 shots. So we multiply by 4 this number of shots. The first thing we notice is that the shaded area of the hardware in high efficient result in green are much larger than the shaded area of the gray, which denotes that the optimization issues themselves, so the fact to have different random initial guesses that lead to different results, has more importance than the noise itself. Like in the gray, it's a basic but quite interesting evaluation on what is only the noise impact on the quality of the result, on the variance. And we see that this variation, so this amplitude of error, is much more thin than the hardware efficient in gray, which denotes that there is both noise during the optimization, but also due to the initial guesses. So this is something we numerically quantified in the paper, and we quantified that the errors given by the optimization issues themselves are larger than the given by the noise itself. And combining the two is increasing the two, okay. When going from 1024 shots to 4096 shots, the hardware efficiency, so in green, the left curve, we see that there is a small offset of decreasing. The average is decreasing by a small order of magnitude, very small. However, in the gray case, it's not changing so much. And maybe the more important value here that I'm saying at the end is that these results, you see that they are quite horizontal, which directly means that, as we confirmed before, the T1 noise has no impact on the hardware efficient results, and changing from 1000 or 50 microseconds of T1 to very large values of T1 doesn't change the quality of the result of the hardware efficient result, which, okay, confirms that it was hardware efficient. Now I'm going to speak about the right curve on UCC results. So here you see that the shaded area is very, 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 very small, and you can almost not see it for the second row here. However, there is a clear evolution with T1. This clear evolution with T1, we can understand by the fact we established before. UCC is not at all, is very robust against shot noise and very dependent on the hardware noise. And we see that it's a very clear dependence. And this very clear dependence, we extrapolated it, and we obtained that for 8-qubit systems, so very small systems, regarding what we want to accomplish in the chemistry side. This 8-qubit system, taking a UCC SD circuit, requires T1 values, so the coherence characteristic time of at the order of magnitude of 4 seconds, or let's say the second. But this is 4 orders of magnitudes larger than the actual hardware decoherence time of IBMQ, for example, which are around 100 microseconds. So to have chemical precision on UCC result on an 8-qubit system, one would require 4 order of magnitudes larger T1 noises, which gives an overview of how much should we improve both the hardwares, but also the method, which are not as efficient as we can expect at this time. The other part which is important here in these figures are the stars that you see, and that are plotted with a whisker. So the stars are IBMQ real experiments. So what we made here, we processed the VQA algorithm fully on a noiseless regime, and we took only the last step, so the final step, the final energy with the final parameters, and we executed these final parameters on the quantum computer of IBM. It was IBMQ Toronto. The star is an average of 10 times of this experiment, and the whisker is the min-max amplitude of these 10 experiments. So here, like this, at this scale, we see that the result seems to be a bit decorrelated, although there is a small overlap on the hardware efficient side. So the noise model is a bit incomplete. So it was already difficult to simulate, because I can note for people which are listening this talk that if you want to model the same noise that we model on 8-qubit system, it's more or less equivalent than making a 2 times number of qubits noiseless simulation. So if I just say it more simpler, with a simpler way, modeling the noise, the hardware noise and shot noise as we made on the 8-qubit system, will take you the same amount of time than proceeding a 16-qubit noiseless simulation. And same for bigger number of qubits. So that's why we worked only with 8 qubits when dealing with the noise inference, because making more qubits was very, very difficult in terms of calculation time. So I was saying that you see a bit, well, not a bit, but you see a clear difference between the results modeled and the real experiments. And this we can explain by the connectivity. So in our noise model, we did not specify the connectivity of the qubits. And when creating a circuit, we were supposing an all-to-all connectivity, which is not at all the case on real hardware. And given the fact that when you go from a not all-to-all connectivity to a all-to-all connectivity, you have to add a lot of CNOT gates. Well, you have to add a lot of swap gates that contains a lot of CNOT gates. That will make your noise much larger and make your noise model valid, but not as well as you can expect. But these were result only at the equilibrium. And why I'm saying that it's not as bad as we can see here, you can see that on the next slide. So here we went from this noise to studying the noise influence only around the equilibrium to analyzing it, for the whole distortion one as we did before. The orange dash curve is an average of 50 VQE experimentation with the noise model that has parameters close to the IBM-Q1 and with shot noise. So first row is 1024 shots, second row 4096 shots. Left column hardware efficient results, right column UCC result, still on 8 qubit system. And the reference of energy, so the zero of energy, are the exact energies that we want to reach, obtained through a diagonalization of the Hamiltonians. And here we don't see the same information than before. Okay, at some point we can have a clear difference between the noise model and the numerical output we obtain from the IBM-Q. However, you see here that the stars and the whiskers, which are the IBM-Q experimentation, the same than before. So making the VQE fully on noiseless regime, taking only the last parameter and doing that on the real QPU 10 times and calculating the average and the min-max amplitudes with the whisker and the stars. We see that if the average are not overlapping, the min-max are clearly overlapping. And this through all of the distortions. So for some points, and especially here on the hardware efficient side for this conditions of shot noise, we have no overlap. However, we are able to recover the same noise influence through the whole distortion. We have the same shape of the curves. And on UCC case, it's even closer. This is also a very interesting result that we obtained. Like, our noise model is still incomplete. However, it allows one to recover the influence of noise through the whole distortion. And you see that it differs by kind of a constant here because the shape is the same. So the talk is now finished. Thanks for your attention. The library D4.2 is available on GitHub, and you can very easily retrieve all of the results we obtained in this manuscript with this library. So as I said, the noiseless results instantaneously, well, depending on the platform you are using, but in terms of code, it's almost instantaneous. The QPU results, you just have to have IBM-Q access, create your QPU bridge between the IBM-Q platform and the simulating platform you have. It will be automatically done. And for modeling the noise as we made, you can see the parameters we used on the paper, and you have the documentation of Atos that allows you to model this very easily with 2 or 3 lines. And what I can also say is that the structure of the code with these 2 scripts, GitHub calc.py, GitHub calc.energy.py, allows you to decompose the VQ algorithm and to combine it maybe with other methods. Thanks for your attention.
Thank you, Wassil, for sharing your research with us. It's always interesting to have an author comment his publication, and I hope this will inspire others, especially our attendees, to experiment too. So it's time for question. Can you go into the next slide, please, Wassil? And it's time for questions, so you can ask your questions in the chat, or you can raise your hand if you prefer. In any case, yeah, just two things. The slides will be emailed to all after the webinar, and this webinar is being recorded, and the recording will be available on our NEASQC YouTube channel. So if you missed part of the presentation, you'll be able to catch up. So we already have one question in the chat. So I will speak it aloud, or you can all open the chat. So the question is, have you tried Adapt VQE?
So with this library, you can use VQE also very easily by just changing the GitHub Calc energy.py part. So instead of taking a fixed ansatz, you can very easily create an iterative ansatz that is created by the criteria you want, the energies, the gradient selection. You can implement this. So we tested it a bit, but VQE has some problems which are different than VQE, is that it will require a lot of VQE, not VQE, sorry. I'm not allowed to disclose everything, but VQE will have a lot of shortcomings on the resource requirements. So when you are proceeding the VQE on the platform on small molecules, it will work. But if you use the basic or the original VQE on a real platform for intermediate size system, let's say, you will see that the number of iterations, the number of times you require a calculation of psi h psi is going to explode with the number of qubits and with the number of operators you require in your ansatz.
Thank you. And thank you, Robert, to Robert Wong for the question. So any other question, please put it in the chat or raise your hand. I have a question to you, Wassil. I mean, what's next? What do you think should be done next so that this can be used in practical use cases?
So as far as I'm concerned, so I think that there is two ways of improvement. So as the previous question said, thanks for this question. Improving the ansatz part. So VQE can be a solution, but it has to be more powerful even than the simple VQE or other methods. These are compatible with that library. Like the library is not going to be vanishing if there is new methods because of this. Those scripts, you can either change it very easily or take only one part of the script and combine it to another. So there is this energetic part. The GitHub Calc energy.py script can be improved with new methods, with new techniques that could allow to tackle much larger systems with less resources. So this is an area of improvement because intermediate size system and so real industrial cases would require much more resources, so much more efficient methods. And also on the GitHub calcamil.py script, you can also not use it, use something else. For example, if you want to work with embedded methods, you want to have some specific Hamiltonian that comes from an embedding strategy. This is compatible with that library. So this can be also a strategy, even if it will be also requiring a lot of work to make it work for bigger systems, but working on methods of fragmentation or how to decrease the size of a system without losing too much information about that can be also an area of improvement, and it will be implemented on the GitHub calcamil.py script or related to the script.
Okay. Well, thank you. Thank you, Wassil. So last call for questions. We still have time. So if you think of a question, please put it in the chat. Meanwhile, can you go into the next slide, Wassil? So
Yeah.
I'll do my promotion while waiting for a last question. So we have our next webinar will be on the 7th of November about quantum probabilistic safety assessment, a perspective within the NEASQC era. So if you have an interest in QPSA, please register, or if you know people, other students, people interested in this subject, please forward the invitation to them. So no more questions? No? Well, that's a pity. Wassil, is there anything you wanted to add before we close today's session?
No, if someone wants to investigate the virtual algorithm, to start with it, to start with this method, because these are the first step in doing quantum computer for chemistry, this library will help you because it will help you to understand how it works and to retrieve the results we published very easily. And if you have questions, I could ask by email without any problem.
Yes, if you want to contact us, really feel free to do so. You can contact us either through our website, neasq.eu. We have a contact form. I get the contact forms. I will point you to the right person. I think there should be a contact email in the invitation you received today. So feel free to, sorry. Really feel free to contact us. We look forward to having your comments and your feedback. So I think I will close for now since we have no more questions. Yeah, I was checking. So thank you for being here today, and I hope I will have the opportunity to talk to you again at a coming NEASQ webinar. I hope you enjoyed this talk, and let's keep in touch. Bye-bye. Yeah, and I forgot to thank Wassil for his presentation. That's really bad.
No
Thank you,
problem.
Wassil.
Thank everyone for the attention. Thank Pascal for this NEASQ meeting. And yeah, let's keep in touch. See you.
Bye.